Let's talk about the hidden language that pretty much runs our world, statistics. Seriously, it's the science that turns mountains of messy data into everything from life-saving drugs to figuring out which movie you're gonna love next. So, how does it all work? Let's find out. Think about it. We are just flooded with information 24/7. So, how in the world do you cut through all that noise? How do you tell what's real and what's just made up? Well, that is the exact problem that statistics was invented to solve. It gives us a reliable way to find the truth that's hiding inside the numbers. To find your way around, you need a map. And in statistics, our map is basically split into two big continents. First, you've got descriptive statistics. This is all about telling the story of the data you already have. It's the what happened. Then there's inferential statistics. This is the really cool part, where you use that data to make educated guesses about the future, the what's gonna happen. Okay, so let's start in that first world, describing what we see. This is all about taking a huge, messy pile of data and, making some sense out of it. So imagine I just hand you a spreadsheet with 1,000 different numbers on it. Where would you even start? Well, the very first thing a statistician does is try to find the center. It's like finding the heartbeat of the data, that one typical value that can kind of represent the whole group. Now, the most common way to do this is with the mean, which is just the fancy word for the average. You add them all up, divide by how many there are. Super simple, right? But it has a major weakness. Think about home prices in a neighborhood. If just one billionaire builds a crazy mansion there, that one super high value can yank the whole average way up, making the neighborhood seem way richer than it actually is. And that's exactly why we have the median. To find it, you just line up all your numbers from smallest to largest, and you pick the one that's smack dab in the middle. That billionaire's mansion doesn't really affect the median, because it's just one house at the very end of the line. This makes the median way more reliable, or what we call robust, when you've got those crazy extreme values. You can really see this in action when you look at a chart. See, in a perfectly symmetrical distribution, that classic bell curve shape, the mean and the median are right on top of each other. But when you have outliers, like in this chart that's skewed to the right, you can see how the mean gets dragged way out towards that long tail, while the median just stays put in the middle. But knowing the center isn't the whole story. Not even close. Imagine two cities that have the exact same average temperature. One could have perfect mild weather all year round. The other could have brutally hot summers and freezing cold winters. To understand that difference, we use something called standard deviation. It just tells us how spread out the data is. A low number means everything is nice and consistent. A high number means your data is all over the map. So we've got a handle on how to describe the data we can actually see. But what about all the data we can't see? Well, this is where we take a leap of faith, a very calculated one, of course, into the world of inference. To make this leap, you gotta understand two key ideas. First, there's the population. That's the entire group you want to know something about, like, say, every single voter in a country. Now, obviously, we can't talk to everyone, so instead, we study a sample, just a small, manageable group that represents the whole. It's like tasting a giant pot of soup. You don't need to eat the whole thing to know if it's good. You just need one spoonful, as long as that spoonful has a little bit of everything in it. Right? But how can we be so sure that our one spoonful really tells us about the whole pot of soup? Well, the bridge that connects our little sample to the big population is built out of probability. It's the mathematical language that lets us measure our uncertainty and say exactly how confident we are that what we saw in our sample is true for the whole group. Okay, so with probability in our back pocket, we can now get to the most exciting part of statistics, actually testing our ideas and making predictions about how the world works. We do this with a process called hypothesis testing. Yeah, it sounds super intimidating, but really it's just a structured way to test an idea. You start with something called the null hypothesis, which is just the boring default assumption, the idea that nothing interesting is going on. Then you go out, you collect your data, and you see if what you found is surprising enough to make you say, you know what, I don't think that default idea is true anymore. So how do we actually measure surprise? We use a little something called a p-value. The easiest way to think about the p-value is as a surprise index. It tells you the odds of seeing what you saw if that boring default assumption was actually true. So a really, really tiny p-value means your result is super surprising and probably not just a random fluke. And that leads us to a simple little rhyme that statisticians love. If your evidence is surprising enough, meaning your p-value is really, really low, then you have a good reason to reject that default, boring assumption. Just remember this. If the p-value is low, the null must go. Okay, but as we start finding all these exciting relationships in our data, we have to be so careful. This brings us to probably the single most important warning in all of statistics. Correlation does not imply causation. Just because two things move together doesn't automatically mean one is causing the other. Here's the classic example. If you look at the data, you'll see a super strong connection. When ice cream sales go up, the number of people who drown also goes up. So does eating ice cream make you drown? Of course not. And this is the perfect illustration of the point. The two things are definitely correlated, but there's a hidden factor causing both of them, the summer heat. When it gets hot, way more people buy ice cream and way more people go swimming, which sadly leads to more drownings. You've always got to be on the lookout for that hidden cause. Avoiding traps like that one is so important. And really, that brings us to the whole point of all of this, building a practical toolkit so we can make smart, confident decisions that are actually backed up by evidence. Let's see how we pull it all together. The great news is you don't have to reinvent the wheel every time you have a question. Statisticians have already built a whole toolbox of tests, each one designed for a specific job. The kind of question you're asking, like, are you comparing two groups, or maybe you're looking for a relationship between different categories, that's what tells you which tool to grab from the box. Choosing the right one is what makes sure your conclusions are actually solid. And that right there is the key takeaway from all of this. You don't have to be a math whiz. The real power comes from understanding the logic behind these tools. It's what lets you make decisions based on solid evidence, instead of just a gut feeling. It's all about knowing which tool to use and why. So, from finding the center of our data all the way to testing our biggest ideas, we've really covered the basics. You now have a map to this incredible world of data. The only question left is, where are you going to explore first?